It's science, but not as you know it. The Naked Scientists.
Hello and welcome to The Naked Scientists with me, Ben Valsler, and with Dave Ansell. Hi, Dave.
Hi there.
This week sees the 150th anniversary of Charles Darwin presenting his theories to the Linnaean Society, so we're looking at the science of evolution. We'll be finding out why scientists have revisited a textbook example of evolution in action, and we'll be discovering why being the horniest sheep may not be best.
Plus, we'll be looking at Darwin's own letters to get a behind-the-scenes look at the man himself. And we'll also be finding out why bacteria evolved in the lab can outcompete their parents.
So they actually grow close to twice as fast as did the ancestor. So when you compete them, the evolved bacteria kick butt.
Now, Dr. Chris isn't with us this week, as his own experiment in genetic recombination, that's mixing his DNA with that of his wife, Sarah, has been a success, and they are now the proud parents of a little boy, Timothy, a brother to their daughter, Amelia. So, congratulations, Sarah and Chris, from all of us here at The Naked Scientists.
Indeed, but even in Chris's absence, we'll be catching up on the latest science news, including why ancient poets may have been astronomically accurate and a new way to communicate underwater.
And Diana O'Carroll will be joining us with this colourful question of the week.
Why is copper the metal, copper in colour, yet when in solution with copper sulphate it's blue and copper carbonate it's coloured, and when you do a flame test it's actually green?
That's all to come on today's Naked Scientists. So if you want to get in touch with any questions or comments, you can email Chris at thenakedscientists.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's kick off, as we always do, with a look at the science news from this week. And this is a lovely story about baby crocodiles. Scientists have discovered that baby crocodiles actually talk to each other from inside their eggs in order to synchronise hatching. Writing in the journal Current Biology, Jean Monnet researchers Emily Vernier and Nicholas Mathivon recorded the sounds that are made by a clutch of crocodile eggs in the time leading up to them hatching. They then played these sounds back to another group of eggs that were due to hatch at some time within the next 10 days. Now, surprisingly, most of the eggs actually answered back, and some of them moved around. But most importantly, all of them hatched within 10 minutes of hearing the sound. Now, for a test, the team played random noise to another group of eggs, and they left a third clutch of eggs in silence. Neither of those two groups showed any reaction, and they didn't hatch. So, to find out why the crocodile hatchlings might be showing this behaviour, the team decided to play these pre-hatching sounds, as well as some random noise, to nesting adult crocodiles in a zoo. The adults responded either by digging, by moving, or by intentionally turning their heads towards the egg sounds, but not the other noises. Now, the researchers think that this is a survival mechanism on the part of the hatchlings, so that they time their emergence when adults are likely to be nearby, and the adults can protect them from predators. The authors also point out that birds are known to make noises from the egg that encourage parental care, and as birds are closely related to dinosaurs, birds and crocodiles may have inherited this behaviour from a common evolutionary ancestor.
Right. I guess also if you're an egg and you're about to hatch, it's much better if everyone hatches at the same time, because if you're a predator and there's just one hatching every day, you can get each one and eat them all up. But if there's 20 all hatching all at the same time, you're only likely to get one. So your best bet is to hatch at the same time as everyone else.
Yes, there's definitely strength in numbers, so all of them hatching together would be safer for the brood as a whole.
Indeed. Now, I've got a story about communications. Now, communications on land have come on in leaps and bounds over the last 20 or 30 years. Now, for relatively little money, you can buy a phone which will transmit hundreds of thousands of characters every second, or you can buy a satellite phone, which means you can talk to your mum from the middle of the Gobi Desert. However, underwater it isn't so easy. The problem is that because seawater conducts electricity, it also absorbs radio waves. This means that once you get more than a few metres under the water, there's no point trying to tune into us on The Naked Scientists. Sound waves, on the other hand, will travel through water very well. For example, whales use them to communicate over thousands of kilometres. The problem is echoes, though. Sound waves will bounce off the surface of the water, the seabed, shoals of fish, even layers of change in temperature of the water. This means if I shouted at you, you'd hear a whole series of overlapping versions of my conversation. It would sound like gobbledygook. This means I'd have to communicate very slowly with you to wait for each echo to die down after every word or every little bit of information. However, William Cooperman and colleagues at the Scripps Institute of Oceanography have used a very neat method to get around the problem. If I wanted to send a message to you, first I'd get you to play me two noises, one to represent a 1 and one to represent a 0. I would then record how that sound got to me. I'd reverse the tape and play them back to you. This means that all the echoes essentially cancel out and all the sound arrives at the same time. This means that I could play the two sounds in a pattern to represent a message. This is what William Cooperman has done, and he can now transmit 15,000 bits of information, that's ones of zeros, over 5 kilometres every second, or about 5 kilobits a second, 5,000 bits a second over 15 kilometres, which is 3 or 4 times faster than the normal conventional links. This isn't just important for talking to submarines, because apart from anything else, if you're creeping around in a submarine shouting out to tell you wait, to give you the first signal so you can play the reverse signal back would give away your position. But it could be very important for robots, because we know less about the bottom of the ocean than we do about the surface of Mars, and most of that exploration is probably going to be done by robotic rovers, which of course will be able to have to communicate with the surface or even with each other.
Good stuff, great stuff. Now, a few weeks ago on The Naked Scientists, we followed the story of the Odyssey and how, although the land has changed considerably in the nearly 3,000 years since it was written, the poet clearly knew his geography. Parts of the poem allowed modern scientists to locate the island of Ithaca, even though the island has now been almost entirely swallowed up by its neighbour. It seems that the poet was also astronomically accurate, as researchers from Rockefeller University report in the PNAS journal. Homer accurately describes a total solar eclipse, even though it happened nearly 3 centuries before they think the poem was ever written. The passage reads, "The sun has been obliterated from the sky, and an unlucky darkness invades the world." A pretty good description of eclipse, I think you'll find, but was it just artistic licence, or were they describing real events which occurred during Odysseus' long journey back to Ithaca? To find out, Constantino Baicuzzi and Marcello Magnasco searched the text for additional astronomical clues, such as which planets were visible at the time and which stars the heroes used to navigate by. The big clue was a reference to the westward flight of the god Hermes, who represents the planet Mercury. Now, Mercury appears quite low in the sky, and it reverses its course, east to west or west to east, every 116 days. Baicuzzi and Magnasco could use all of this data together to scan all of the possible dates that fit all of these conditions. Now, they knew that in order for a total eclipse to occur, you must also have a full moon. And all of these conditions only occur together once every 2,000 years. One of these matches is the 16th of April, 1178 BC, which fits exactly with Odysseus' 10-year journey home from Troy. Now, we'll never know if the events described to have taken place really happened during the eclipse, but it seems the description of the eclipse itself was more accurate astronomy than artistic artifice.
Interesting. It's amazing how accurate sort of vocal traditions can be in this sort of situation. You can get a story which was preserved over hundreds of years. Once it started, quite often it'll keep on going very accurately. Now, you're talking about Mercury there. Now we're going to go on to Mars. NASA's Phoenix lander, which landed on Mars about a month ago, has started giving us our best view of the Martian soil yet. The lander is sitting on a plain near Mars's northern ice cap and has been digging the soil and measuring its properties. After some problems in getting some soil inside its analysis machine, as it was too clumpy, the thermal and evolved gas analyzer run by William Boynton, who was on the show a few weeks ago, has heated some soil up to 1,000 degrees centigrade and measured and analysed the gases coming off. They're still working on that analysis, but apparently the soil has definitely interacted with water in the past. And the Microscopy Electrochemistry and Conductivity Analyzer, or MECA, has been given a microscopic view of the soil and mixing it with water to try and understand the chemistry of the soil when it's wet, what's dissolved in it and things like that. This is the first wet chemistry experiment done on any other planet than Earth, and the results show that the soils are very like some Antarctic dry valley soils very high up in the mountains in Antarctica without any snow on them. They've found some useful nutrients like magnesium, sodium, potassium and chloride. They're still analysing the data looking for others, and the pH is between 8 and 9, making it quite alkaline, but about right for growing cabbages.
Well, those would be some cabbages with some extreme food miles, probably not the best ones if you're trying to go green.
Indeed.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
You're listening to The Naked Scientists with Ben Valsler and Dave Ansell. We're discussing the science of evolution today, and we'd love to hear from you, so please get in touch with any questions or comments. The email address is chris@thenakedscientist.com.
Now, still to come on today's show, we'll be finding out how scientists have revisited a textbook example of evolution, the peppered moth, and we'll find out a bit about Charles Darwin's personal life as told in his own words.
But first, we've got an interesting kitchen science for you to try at home, all about the physics of temperature. If you want to have a go, then all you're going to need is some ice cubes, a plastic or wooden chopping board, and a metal frying pan.
Hello and welcome to Kitchen Science. Today we're at Sir John Lawes School in Harpenden. I'm, of course, with Dave Ansell.
Hi there, Ben.
And I'm also with Martin.
Hello.
And Nihal.
Hi.
And we're out in the garden here, but Dave seems to have brought some kitchen equipment with you. What are we doing today, Dave?
Doing quite an interesting experiment on temperature.
On temperature. So it seems appropriate that it's quite a nice sunny day out here. What do we actually need to get to set this up?
Well, you want a saucepan or a frying pan or something with a nice thick bottom, a chopping board, and a couple of ice cubes.
OK, well, this doesn't sound like a very tasty meal.
I'm afraid it isn't, Ben. You have to wait for supper.
So, assuming that we've got a metal saucepan or frying pan and a chopping board, I can see you've got a plastic chopping board. Would it work with a wooden one?
Yeah, something like that, as long as it's not metal or stone.
So once we've got this stuff together, what do we need to do?
Well, the first thing I want Nihal to do is to feel the chopping board and the saucepan and tell me which one feels the coldest.
OK, so if you could feel them both for us.
Okay. The chopping board is warmer.
So the chopping board feels warmer than the saucepan?
Yes.
OK, well, they're both in the shade, so they're not being heated up by the sun. Is that about right, Dave?
That's what they normally feel like, yes.
And again, would the same go for a wooden board?
A wooden board would feel warmer than a saucepan normally, yes.
That doesn't seem like much of an experiment.
OK, then what I want you to do is get 2 ice cubes, put one on the chopping board and one on the saucepan and see which one melts first.
OK, so Martin, would you mind... We've brought some ice with us. Yep. So would you mind grabbing some ice from the bag and putting 1 cube on the chopping board and 1 on the saucepan?
Yes, sure will do. Actually, you can open. There you go. Right, it's just 1 on each.
So 1 ice cube on the saucepan and 1 on the chopping board.
There you go.
OK, so they're in place now. Now, what do you think will happen? Which one do you think will melt quickest?
Well, the chopping board's warmer. You just thought the chopping board would.
Do you agree?
Yeah, the chopping board, definitely.
OK, well, we are going to leave these ice cubes to melt for a while now, and we'll come back to you later on in the show to let you know what happened.
So if you want to have a go, grab some ice cubes, put one in a frying pan and another on a chopping board and see which melts first.
Now, one other very exciting thing that we do here on The Naked Scientist is to beam this programme directly into Second Life. So from 6 p.m. UK time, which is 10 a.m. Second Life time, if you want to come and find us and meet some of our other listeners, you can meet them there. Hello, everyone in Second Life. Go to Second Life, visit the Scilands continent and search for The Naked Scientists. Drop by our mansion, relax on the sun loungers and enjoy listening to the show.
Laying the facts bare, The Naked Scientists.
This is The Naked Scientist, and today we've naturally selected to talk about evolution. Now, one of the more elegant examples of evolution you'll find in textbooks is that of the peppered moth. Dr. Remy Ware is from the Department of Genetics at Cambridge University, where they've been going through the experiments that got the peppered moth in the textbooks. Hi, Remy.
Hi there.
Now, first of all, can you tell us what the original story was?
Yeah, sure. So originally there was an observation made in 1848 in Manchester in which there was a dark form of the so-called peppered moth first recorded. Now, the peppered moth, its normal form is sort of light in colour with a black speckling, which gives it its name. And in 1848, the first black or melanic form of this moth was recorded. And towards the end of the 19th century, towards about 1895 or so, a very large proportion of the moths found in Manchester were of this darker form. And a very distinguished Victorian lepidopterist called J.W. Tutt proposed the hypothesis for why this was occurring. And his hypothesis was one of differential bird predation. So the idea was that with the Industrial Revolution, the pollutants produced, such as sulphur dioxide and soot fallout, had darkened the surfaces of the trees on which these moths rest. So a combination of killing off the foliose lichens on the trees and actually darkening the surfaces themselves meant that what was previously a well-camouflaged light moth on a light surface now stood out very conspicuously to predators and suffered a higher predation rate, such that a new mutation causing a melanic variant of the moth was at a greater advantage through being more cryptic on the surface. Following this hypothesis, a chap called Bernard Kettlewell through the 1950s started trying to really test what was going on here.
Okay, so basically the birds, if you're flying along and you see a black moth on a black tree, you're not going to have seen it, whereas all the white ones are going to get eaten really quickly.
Simply a case of looking cryptic against your background. So being light and camouflaged on a light surface, or being black and camouflaged on the blackened surface.
So more of the black ones survive, so they're more for the next generation, so there's just going to be more and more of them around after a few generations. Yeah. There's been some criticism of this experiment. What was that?
Okay, so this chap Kettlewell started trying to test the hypothesis of this bird predation, and more recently, over the past decade or so, his work's been criticised, mainly because of issues to do with it being very artificial. Now, what he actually did was he had an experiment in which he looked at an oak woodland in Dorset and a polluted woodland in Birmingham, and he looked at the levels of predation of the different forms of the moth, the light form versus the dark form. And he found a reciprocal result in these experiments, in that more of the dark form were predated upon in the lighter area. And the criticism of this really is that it was rather artificial for many reasons. Firstly, he was using a mixture of lab-bred and wild-caught moths, so they may not be behaving naturally. And also he was placing them on very conspicuous positions on the tree. And
so the natural moths would have hidden.
Yeah, I mean, later experiments even involved gluing dead moths onto the tree in positions that were rather conspicuous, and actually we know now that moths naturally rest under twigs and under branches and things. And also he's releasing moths in very, very high densities, so essentially he was creating what we call a bird table effect. So the birds were learning that they come to this site and they've got a good lunch straight away. So it was really these criticisms of artificiality which have been at the forefront of the argument against the peppered moth case.
So I guess he was still showing that there was a selection pressure towards the dark ones in the dark trees, but light ones in the light trees, but people weren't entirely convinced.
Whatever the criticisms of it being artificial, it was the reciprocal nature of the results in the two areas that was so convincing. Never mind the sort of nitty-gritty of the quantitative accuracy of the case. Qualitatively, it seemed very convincing, and subsequent evidence came from a reduction in the dark form of the moth following anti-pollution legislation later on. And so this was rather convincing and shows, importantly, that evolution's not a one-way process, and it can go back.
So you've now been looking to try and fix some of the problems with this experiment, to try and silence the critics. So what have you been doing?
Some work led by my colleague Professor Michael Majerus. He wrote a book on melanism in 1998 addressing this point, and since then had a number of criticisms, and so set about systematically trying to correct the problems with the original story, mainly by removing these issues to do with it being a very artificial type of experiment. He tried, as far as possible, to make it a natural experiment. So he was releasing moths in natural frequencies, very, very low frequencies. And this experiment actually took over 7 years to complete because it was trying to be so realistic.
Very patient.
Yeah. Importantly, he also allowed the moths to choose their resting positions naturally. He released them overnight and allowed them to select their positions as they would do in the wild, whereas Kettlewell was releasing them during the day. And so it's quite likely that they wouldn't select natural positions. So various things like this, and natural densities being the reason why it took such a long time to do.
So what was the results of the experiment?
So similarly to what was found by Kettlewell, this work was done in Cambridge, actually at his home, and it was found incredibly convincingly that there was a very strong correlation between observed declines in the dark form in Cambridge. This was between 2001 and 2008. So he found that there was a very close correlation between the decline in the dark form of the moth during this time and the actual predation that he observed by eye. So he observed various birds taking these moths from the trees, differentially with respect to colour form, with respect to black or the light form. And it was a very close correlation between the predicted decline in the dark form as a result of this predation compared to what was actually observed. So it's very, very strong evidence that differential bird predation was responsible for this.
Brilliant. Thanks very much, Remy. That's Remy Ware from Cambridge University on how experiments on evolution can themselves evolve and improve.
Now, still to come on today's show, we'll be learning a bit more about Charles Darwin, as I had the fantastic opportunity to look through some of the letters that he sent and see in his very own words the theory of evolution forming.
But before that, we're looking at evolution on a lab bench. Professor Richard Lenski works at Michigan State University, and in his lab he's grown over 40,000 generations of E. coli for over 20 years. He's persuaded the bacteria to evolve totally new characteristics, giving scientists new insights in how organisms adapt and change over time.
Well, I've always been interested in the tension between evolution being a random process at the level of mutations, and yet natural selection provides a force that moves populations to become ever more adapted. And so this experiment with E. coli has been designed to look at how reproducible evolution really would be if we could repeat it. And so I created 12 lines of E. coli, all started from the same ancestral cell. And we've been propagating them in my lab for about 20 years now, and the bacteria have gone through 40,000 generations, and we're watching how they change and evolve.
What are the advantages of using a bacteria like E. coli to observe evolution in the lab?
One of the advantages of bacteria, of course, is that they have such short generations. Also, they have very large population sizes, so in a little flask in a corner of the lab, we can have millions of cells. And what's really cool to me is that we can freeze the bacteria away. And that allows us to directly compare ancestral and evolved organisms. And we're actually comparing the living organisms. It's not just fossils, it's the real live bacteria. So imagine a little bit like if we could bring Neanderthal back to life. We might try to play a game of football with the Neanderthals, and we could see how the organisms in their performance, not just in their fossil morphology, but in their real performance, have changed over time.
So what evolutionary changes have you seen since your very first cell line?
Well, one of the most important changes is that the evolved bacteria are demonstrably much more fit in this environment. So they actually grow close to twice as fast as did the ancestor. So when you compete them, the evolved bacteria kick butt. The evolved cells are much larger, and we're looking at how they've changed in many, many other properties, but in particular, the last few years, we've been looking at how they've changed in their genotype. So we're actually sequencing their DNA and finding the mutations that are responsible for their adaptation.
Recently, you reported on a rather more dramatic change that had happened, in that they seemed to be able to use a different source of food. What had happened here?
In this medium that we've been feeding them every day for these last 20 years, they've been growing on glucose as the only source of energy that they can use that's in that environment. But throughout this entire experiment, we've had another carbon source that's been present in the medium, and it's called citrate. And one of the features that's been recognized of E. coli cells is that they're not able to use citrate as an energy source. It can't get inside the cell.
So this is one of the defining features that makes them an E. coli bacteria rather than something else?
It is, pretty much. There are little gray areas around the edge that are rather technical, but it's certainly the general property of E. coli, one of the defining characteristics by virtually all assays. And so for 20 years, they've been eating their glucose and not recognizing that there's an open niche, another resource available in their environment. But one of the 12 populations suddenly woke up, as it were, in an evolutionary sense, and said, there's something else to eat. There's a dessert tray around the corner after we finish our glucose. And so that population evolved the capacity to use this new carbon source as an energy source. And what we've done has been to try to ask, could any of the populations have evolved that new trait at any point in the experiment? So we've been trying to ask whether the genetic context changed so that this new phenotype became possible by virtue of the more or less inconsequential differences that had accumulated in one population versus the other 11 populations. And we took advantage of the fact that we have all these time points frozen away in our freezer. And with an extraordinarily dedicated graduate student, Zachary Blount, he essentially went back into the freezer and started the evolution experiments over from different time points along the way to the evolution of this interesting new trait. And what he found was that only after a certain point in time did he ever find mutants that were able to use citrate as a carbon source. So a sort of a historical accident of the genetic changes in one line versus the other lines had opened up this door that there was another possible way of making a living in this extremely simple laboratory environment.
So you need a series of smaller, seemingly irrelevant mutations in order to have this big mutation that lets you change your food source.
Yes, it's very clearly established that there were many mutations in these lines and that some subset of them that occurred in this population set up the potential to then get additional mutations that gave this very interesting new trait or phenotype. And in this simple little experiment that we've been doing in my lab, this one population out of the 12 we've been studying took a different road, got on a different evolutionary path, and that influenced its subsequent potential.
That was Professor Richard Lenski, who's been watching his E. coli evolve in the lab. His work shows that although evolution is often predictable, sometimes all of the little random mutations, which on their own don't amount to much, can allow some big dramatic changes, possibly even leading to the birth of a new species.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
So that was evolution in the lab, but what about in the wild? Our next guest, Alistair Wilson, is from Edinburgh University, where he and his team have been studying the evolution of Soay sheep. Now, the males of these sheep, if you have big horns, it means big success. So the bigger your horns, the better you can compete with other males, and the more likely you are to be able to breed. Now, you might think that the males would have evolved to have the biggest horns possible, but in the unpredictable wild weather, things aren't quite that simple. Hi, Alistair, thanks for joining us.
Hello.
So, what is it that you found with the Soay sheep?
Well, this is, I should say this is work really led by a colleague of mine, Matt, who sadly has gone to Glastonbury today. But Matt decided he wanted to take a closer look at how natural selection is really acting on these traits of horn size and horn growth. As you said, if you're a male sheep, it's pretty important to have big horns because when it comes to breeding time, you actually have to fight with the other males to try and get access to the females. So I guess what he expected and what we all expected was that bigger horns, faster growing horns were going to be better. And it turns out that some of the time that is the case. But there's also kind of another layer of complexity, which is that if you want to grow horns very quickly, you've got to put a lot of energy into doing that. And the Soay sheep live on an island of St Kilda, which is characterised by really quite strong variation in the environment. Every now and then we hit a year where the food kind of runs out and conditions get really, really tough. And it turns out if you've put too much energy into growing horns, then you're very unlikely to get through the winter. So there's kind of a trade-off here. And if you grow your horns too quickly, there's quite a high chance of dying if you hit sort of some bad conditions.
So the sheep are really taking a gamble then, because they know that, well, they know that if their horns are as big as they possibly can be, then they're more likely to have the success in later life. But they are betting on the fact that their first winter will be quite a mild one.
Well, that's it. You can kind of think of it as different strategies. If you have a good season coming up, then it's definitely better to have gone for it in terms of growing your horns. But of course, if you get that wrong, you might end up dead, in which case it doesn't matter how big your horns would have been, because you're not going to get any breeding success the next season.
Now, does this mean that the sheep are either born with the potential to have big horns or born with the potential to survive the first winter?
Well, it's a little more complicated than that, but what we've been able to find is that, yes, there is some genetic variation for these traits, and that translates actually to genetic kind of covariation between the horn growth and the survival. What that means is selection is acting kind of at the genotype. It's not a case of sort of a complete genetic predetermination. These genes will give you faster growing horns and these ones will give you slower growing horns in that sort of categorical way. But there are certainly there's some genotypes that have a tendency to go in one direction or another, and it's this genetic variation that natural selection can act on.
Okay. Now, we've just heard about evolution in the lab, and it's very easy in the lab to control the conditions under which your organisms are evolving. In the wild, obviously, you don't have that option. You can't say, well, it's going to be this temperature this winter. So how do you actually study them?
Well, it's certainly tricky. Obviously, we've learnt an awful lot, and we'll continue to learn an awful lot by studying evolution in the lab. But really what we're trying to do is precisely to tackle head-on those problems of changing environments, because if we want to understand how evolution does occur in sort of the real natural world, then we are actually going to have to work out how we can integrate all these changing environmental variables, as you say, temperature or population size or anything. Fortunately, ecologists have been working for decades on exactly what these variables do and how they affect organisms like our Soay sheep. And so the challenge that we're facing is to try and integrate perhaps what geneticists can do in the lab with what the ecologists are telling us, and to try and integrate these sources of complexity rather than avoid them as you would do in the laboratory.
So can you take a genetic profile of your population and then try and use that to estimate how well they will cope with, say, a bad winter coming up? Can you actually use the genes to predict success?
Well, I think we maybe aren't quite there yet, but that's, I guess, what we're working towards. We're trying to get an understanding of how changes in the environment will affect both natural selection and also the sort of genetic variation for different traits on which the selection can act. And I think really it's important if we can start to understand how environmental change in any form will affect those parameters, then we can actually start to build changing environments into predictive models of phenotypic evolution or evolution of traits.
Okay, so if the climate changes, as we are predicting that the climate should in fact be warming up, would this have an effect? So would we expect to see bigger horns on these sheep as the weather gets hotter?
Well, so certainly like a starting prediction might be that if the weather warms up, we get fewer and fewer of these bad years, and so the net result of that will be that selection generally is going to always favour fast growth in horns, rather than sometimes favouring slow growth. And if that's the case, then we're going to have an increase in, if you like, the net selection for faster growth. And so we would expect evolution towards faster growing horns, yeah.
Oh, well, that's really interesting. So what does this tell us about the way that selection pressures balance each other? Because obviously we have the sexual selection here, which is that you need to have big horns to compete with with the other males around and to actually breed. But we then have the external natural selection. Does one drive the other?
Well, I guess you can look at this problem in different ways. For me, I think of it all as being sort of different components of the total selection. And the key point is that selection can act in different ways through what we might call different components of fitness, whether that be reproduction or survival in your first year versus survival in your second year. So the idea really is that if we can get a handle on how these individuals are behaving throughout their whole lives, across a range of environments, then we can start to see how selection trades off either across different environments, across different ages, or through different components like survival and reproduction. And we can bring all of that together to try and get an idea of the total picture.
So when we say that an animal is fit and we're looking at the survival of the fittest, it could actually be that they would be very fit in one aspect, but that would in turn make them very unfit in another aspect.
That's it, exactly, and it can be a real problem, because sometimes the things you can measure might be survival. It may be much, much harder in your particular system to measure maybe the number of eggs produced or something like that. You can get quite a misleading sort of idea of what selection is doing if you only look at one sort of aspect of fitness at a time. The challenge is to try and get a whole complete picture of an individual's life, perhaps, and how its fitness is achieved through both surviving and reproducing.
Fantastic. Well, thank you very much, Alistair.
That was Alistair Wilson from the University of Edinburgh telling us how young sheep make an evolutionary gamble when they're growing big horns. Big horns could mean more success, but only if you survive your first winter.
The Naked Scientists. For more information, get online at nakedscientists.com.
Now, this is The Naked Scientist with Ben Valsler and Dave Ansell.
We're looking at the science of evolution today, but still to come, we've got our question of the week, where we'll be finding out why copper is so colourful. Also, we'll be going back to Harpenden for the second part of our kitchen science, where we're seeing which ice cube will melt first, the one on the cool-feeling metal saucepan or on the warm-feeling chopping board. Various people on Second Life, Troy McLuhan, Crystal Falcon and Zanzibar Rothschild, are definitely on the right lines. So if you want to get in touch with us for any reason at all about the kitchen science, if you've got any questions about evolution, you can email Chris at thenakedscientist.com.
But first, before we go back to kitchen science, as it's 150 years this week since Charles Darwin presented his ideas to the Linnaean Society, now this marked the first public outing of the theory of evolution, I went to visit Dr. Alison Pern. She's from Cambridge University. I went to see her to learn a bit more about the man behind the theory. Alison is behind the Darwin Correspondence Project, so I started by finding out just what that is.
Well, it's pretty much what it says on the tin, really. There are about 14,500 surviving letters written both by and to Charles Darwin, and we are publishing complete transcripts of all of them. They're available in hard copy volumes, and they are also going up on the web.
But we have the books that Darwin wrote. The books would be the distilled essence of what he wanted to communicate. Why would we need all the letters, all the rough drafts?
The books are meant for public consumption. They are the final finished product. And there's a whole backstory, an extremely interesting story of how those books came into being. Darwin was not a lone genius who suddenly had an epiphany of an idea and immediately wrote it down. He was somebody who worked away for many years in enormous detail. He talks about amassing great quantities of facts. He did that largely through the medium of correspondence, through letters.
Can we trace the development of his theories using his correspondence?
To a large extent, yes, we can. There were certain of his scientific colleagues with whom he did discuss his ideas in a certain amount of detail, in particular in correspondence with Joseph Dalton Hooker, who was director of the Botanic Gardens at Kew and Darwin's closest friend, and with Charles Lyell, who had been an early mentor. It is possible to see Darwin beginning to discuss his ideas and collecting the evidence to support the arguments that he was making.
And Darwin and Wallace presented their ideas together to the Linnaean Society in July 1858. But if the correspondence shows that he was still discussing aspects of it only months before, what was it that galvanised him into presenting his findings instead of the long, painstaking work he'd been doing?
Well, famously, it was the arrival of a letter from Alfred Russel Wallace, who was out in the field in Malaysia. But Wallace had also written a paper which Darwin then describes as being so uncannily like his own theory that in some ways it was as if Wallace had actually seen his manuscript. He actually panicked. He immediately writes to Charles Lyell and to Hooker and really is asking them what he should do. So it was actually Darwin's friends who were pushing him to publish in what to him was an unseemly hurry. In fact, of course, when the papers were read at the Linnaean Society, neither Wallace nor Darwin was actually there. Wallace was still out in Malaysia, and Darwin was struggling with a completely different crisis in his life. 2 of his children were ill with scarlet fever. And through the detail of the letters, it's actually possible to see the alternating hope and despair as the children get sicker. He is explaining to people that he can't respond to their letters, in fact, including Hooker, who is trying to get him to publish because he is completely distracted by the illness of his children. And just 2 days before the joint papers were read to the Linnaean Society, his youngest child, his baby, Charles Darwin, died.
My dearest Hooker, you will, and so will Mrs. Hooker, be most sorry for us when you hear that poor baby died yesterday evening. I hope to God he did not suffer so much as he appeared. He became quite suddenly worse. It was scarlet fever. It was the most blessed relief to see his poor little innocent face resume its sweet expression in the sleep of death. Thank God he will never suffer more in this world. I have received your letters. I cannot think now on the subject, but soon will. I can see that you have acted with more kindness, and so has Lyell, even than I could have expected from you both, most kind as you are. I can easily get my letter to Asa Gray copied, but it is too short. Poor Emma behaved nobly, and how she stood it all I cannot conceive. It was wonderful relief when she could let her feelings break forth. God bless you. You shall hear as soon as I can think. Yours affectionately, C. Darwin.
A personal tragedy like that must have been awful. It must have almost made him give up.
It did. It's only because it was his closest friend who had asked him to send the papers, and a close friend with whom he could discuss his feelings on the death of his child, I think, that he actually was able to send the papers. And he writes, it's a postscript to a letter in which Darwin, as an afterthought, really says, I've just realised that you want these papers now and I'm sending them, but I almost don't really care.
I dare say all is too late. I hardly care about it. But you are too generous to sacrifice so much time and kindness. It is most generous, most kind. Do not waste much time. It is miserable to me to care at all about priority. God bless you, my dear kind friend. I can write no more.
3 days after this letter was sent, Darwin and Wallace's abstracts were presented to the Linnaean Society. How did he react about this? How did he feel?
Well, personal life was still intruding in a very big way. During all this whole period, he was very concerned that the rest of the family might become sick. And he writes to Hooker a few days after the paper. The first thing that he's keen to say is that they have evacuated the children and that they'll move his daughter as soon as she's well enough to go.
So family was still at the forefront of his mind?
Absolutely. In all the letters in this period, once the first child has become sick, it's the family that are there first. It's the first thing he mentions in letters to everyone he's writing to at this point. But he does thank Hooker very sincerely for having watched his back, really, and gone to so much trouble to make sure that his name was associated with Wallace's in the reading of the papers, although he says really he's rather ashamed of himself now for having cared about whose name was given priority.
My dearest Hooker, we're becoming more happy and less panic-struck now that we have sent out of the house every child and shall remove Etty as soon as she can move. You may imagine how frightened we have been. It has been a most miserable fortnight. Thank you so much for your note, telling me that all has gone on prosperously at the Linnaean Society. You must let me once again tell you how deeply I feel your generous kindness and Lyle's on this occasion. But in truth it shames me that you should have lost time on a mere point of priority. I do not in the least understand whether my letter to Asa Gray is to be printed. I suppose not, but I'm quite indifferent, and place myself absolutely in your and Lyle's hands. I can easily prepare an abstract of my whole work, but I can hardly see how it can be made scientific for a journal without giving facts, which would be impossible. If the referees were to reject it as not strictly scientific, I would perhaps publish it as a pamphlet. We would thank you heartily for your invitation to join you. I can fancy nothing which I should enjoy more. But our children are too delicate for us to leave, and I should be mere living lumber. If you see Lyle, will you tell him how truly grateful I feel for his kind interest in this affair of mine? You must know that I look at it as very important, for the reception of the view of species not being immutable, the fact of the greatest geologist and biologist in England taking any sort of interest in the subject, I'm sure it will do much to break down prejudices. Yours affectionately, C. Darwin.
So the tragic events in Darwin's personal life almost stopped his work on evolution from ever seeing the light of day. That was Alison Pern from the Darwin Correspondence Project, with samples of Darwin's own letters voiced for us by Malcolm Love.
And now it's time to introduce a pinnacle of evolution. It's Diana O'Carroll with a colourful question of the week.
What an introduction. Thank you, Ben. Anyway, back to more serious matters, of course. This week we'll be exploring the psychedelia of copper.
Hello, my name is Vivian. I'm calling from Adelaide in South Australia. And my question is, why is copper the metal, copper in colour, yet when in solution with copper sulphate it's blue and copper carbonate it's coloured, and when you do a flame test it's actually green?
So how is it that one metal is so different in colours from the others to start with, and what makes its compounds so much more exciting to the eye?
Hello, I'm Dr. Peter Wathers, and I'm a teaching fellow in the Department of Chemistry at Cambridge University. Now, metals in general reflect all of the light energy that comes onto them, but copper doesn't reflect all of them. It actually absorbs part of the spectrum. It absorbs the bluey part of the light and maybe some of the green light, but reflects all the coppery-coloured light, which comes back into our eye. So that's what happens with the metal. Now, in compounds, copper sulfate, the blue colour, is due to the light energy being used to promote or excite electrons that are in the atom of the copper when it's combined with other things such as the sulfate or carbonate ions and so on. So in solution, what you actually have, in the same way that when you dissolve salt in water, you end up with sodium ions and chloride ions, not bound together any longer as they are in the crystal, but surrounded by waters. Well, the water interacts with the copper ion. The colour that you see there isn't really copper sulfate any longer. It's copper ions surrounded by lots of water. Copper carbonate, the solid, doesn't have the same water there, and this is usually sort of a greenish colour. Incidentally, the copper sulfate, the crystals itself are blue, but that's because they also have water trapped into their crystals. But if you heat them up and drive out the water, they actually go white and colourless. So it's the waters there that are interacting with the copper ions. Finally, the flame test. Why does the element test produce a green flame? Well, this again is energy being used to excite the electrons in the atoms or ions. And then when this energy is returned, is given out again as the electrons fall back down to their low energy levels, it gives out only part of the spectrum, and it gives out pure green light.
So the different electron configurations in copper leads to a more exciting selection of colours. When light, an electromagnetic wave, hits the copper atoms, it creates an electric current and the light is re-emitted. Copper atoms are special in that they have a reduced reflectivity at the blue end of the spectrum, producing reddish-gold colours. With each new copper compound, the electron distribution is reconfigured and new colours are produced.
And Soul Surfer at the nakedscientist.com/forum hit the nail on the head, saying that compounds will have different absorption spectra compared to the elemental form, and so have a range of different colours.
Anyway, if those colours are too bright, why not get some shut-eye and explore the next question?
Hi, my name is Paula Ovi. I'm from Johannesburg in South Africa. My question is about dreams. I was wondering why it's so difficult for us to remember our dreams when we wake up in the morning.
And take a deep breath for this next question.
Hello, my name is Jason Flakes, and I'm calling from Annandale, Virginia. My question is how is it possible for a bornene flat-headed frog to have no lungs and breathe through its skin?
So if you know why we forget dreams immediately after waking, or how a frog survives without lungs, then get in touch by emailing questionoftheweek@thenakedscientist.com or join the discussions on our brilliant and shiny forum at thenakedscientist.com/forum.
Thank you very much, Diana. We shall see you again with Question of the Week next week.
It's time now to go back to Hertfordshire for the result of this week's Kitchen Science. Which ice cube did you think would melt first?
Well, we've had a lot of comments from Second Life on this one. Troy McLuhan thought that the saucepan would conduct heat faster. Now, I'm guessing he means that it'll melt quicker. Zanzibar Rothschild also thought that the saucepan ice would melt quicker as they are designed to distribute heat. And it seems that Crystal Falcon actually did do the experiment while she's in Second Life. I'm guessing she did it in real life. And she said that she glanced back at the ice cubes. The one in the pan had completely melted, but the one on the cutting board was only a bit of a puddle around it. So it seems that the one in the pan was melting quicker. So let's go back now and find out what we saw. Welcome back to Kitchen Science at Sir John Lawes School in Harpenden. I'm still with Dave, Nihal and Martin, and we've got a chopping board, a saucepan and some ice. Or rather, we did have some ice. The ice seems to have melted. Nihal, on which one did the ice melt first?
On the saucepan.
And is this what you expected?
No, we expected the ice on the chopping board to melt faster.
OK, Martin, any idea why it might have melted quicker on the saucepan?
Well, I'm guessing the plastic must be an insulator and the metal must be a conductor.
That sounds like a very likely answer. Dave, is that right?
Yeah, that's exactly right. Metal is a good conductor of heat and electricity, which means that when the cold ice cube sits on top of the saucepan, lots of heat energy will conduct through the saucepan into the ice cube, melting it quite quickly. Whereas the chopping board made out of plastic is a good insulator, so it takes a very long time for the heat energy to conduct into it, so it doesn't melt nearly as quickly.
But when we checked them both earlier, the chopping board felt warmer. Now, surely the warmer thing is going to get the ice to melt quicker.
They were both actually about the same temperature. It's just that the saucepan felt colder. So when you put your warm fingers onto it, it conducts heat away from your finger much quicker, so your finger gets colder. Whereas if you put your finger on the insulator, even though the insulator's quite cold to start with, you just warm up a little bit under your finger, and your finger doesn't get very cold because you can't conduct the heat away. So your finger stays warm, so it feels warm.
Well, that's really interesting that it doesn't conduct heat away, and so it feels warm. Do we use this anywhere else?
Well, if you want to keep a cup of coffee warm or something like that, you want to surround it in a good thermal insulator so the heat can't get out, so your coffee will stay hot for as long as possible. So they often make little coffee cups out of expanded polystyrene, which is a really good insulator. Or if you want to get heat away from something like a computer chip, put a big heat sink on the top made out of something which conducts heat really well, like copper or aluminium.
So if metal conducts heat away more easily, then why, in my thermos mug that I have at home, why is it lined with metal?
Well, firstly, your thermos mug is probably made out of a metal which doesn't conduct heat very well, like stainless steel, as opposed to copper, which is a really good conductor. And also it's made out of two very thin layers of steel with a gap in between. and they've probably pumped the air out of the gap in between, so you can't transfer heat through it via the air. And it's also very shiny, so it will reflect any light, which can also transfer heat very well. So it should insulate well.
So my thermosmug has very thick walls because there's one layer of steel and then a layer of vacuum which doesn't conduct heat very well, and then another layer of steel on the outside.
Yeah, that's right. This experiment also shows why thermos flasks can keep things both hot and cold, because basically it's a very bad conductor, so if you put something hot in it, it will stay hot. If you put something cold in it, it will stay cold.
Well, thank you ever so much for helping us with our experiment this week.
Oh, thank you very much for having me. It was much appreciated.
And Martin, thank you.
Yeah, thanks a lot. It's good fun.
And that's all we have for Kitchen Science this week. We'll be back with more very soon.
Indeed, and Nihal and Martin took time out of their chemistry mock exams to join us with this Kitchen Science, so I hope they did well in their real ones.
They should be fine as long as the questions were about insulators and conductors and how they affect the rate of ice melting. But they may have had this question in their exam, and this has come in from Crystal Falcon in Second Life. She's the one who did the experiment and got it spot on. Well done, Crystal. She asked if it would apply to dry ice in the same way. Dave?
Basically, yes. Dry ice is when it doesn't actually melt, it sublimes straight to a gas, to carbon dioxide gas. And that takes energy, so the more energy you can get into the lump of dry ice, the quicker it will sublime away to nothing. And something metal will conduct heat in much quicker. And it's something I've done in the past, because if you get a metal spoon and squash a piece of dry ice, then it sublimes much quicker and you get lots of gas given out, and it makes a nice squeaking noise.
Good stuff, good stuff. Well, Remy Sings, we still have you here. We've had a question for you also from Second Life. And he was saying, if you looked at the genes of the peppered moth, what would you see? What would be the differences between the two colours?
That's a great question. Indeed, this crucial genotype-phenotype link is what we're after, really, in evolutionary genetics. As yet, we haven't really looked in much detail at the genome of the peppered moth, but what is quite promising is that we have very good sequence data for a number of sort of related Lepidoptera species, such as the commercial silkworm Bombyx mori, and also some of the Papilio butterflies. Now, their genomes are quite well studied, and it's possible that we can look for candidate genes within those and then transfer it. But a similar approach has been used in another species which shows melanism, the rock pocket mouse, which is a lovely little thing found in North America. And you have a melanic variety of this mouse which rests on a dark surface produced by larval flow, compared to the normal form, which is a sort of fawn colour. And in this species, they've actually found the gene responsible for this polymorphism. They found the gene responsible for the melanism, which is due to it's called the melanocortin-1 receptor gene, and it's this particular gene that's mutated in the dark form of the mice. So that's an example where we do have this link between the genotype and the phenotype, and indeed that's rather often used as a criticism of the peppered moth case, in that's lacking. So the concept of being able to identify exactly what's going on genetically is really exciting.
Excellent. Well, it's obviously very important to make the link between genotype and phenotype. Now, if I'm right, genotype is what the genes actually show you, and phenotype is what we see on the outside. So phenotype would be the fact that it is a dark mouse.
Yeah, so a phenotype is produced both by the action of genes and the action of the environment. So the phenotype is sort of the physical manifestation of different factors causing a particular trait, so both genetics and environmental factors.
Fantastic. Well, thank you ever so much for joining us, Remy.
Thank you for having me.
I'm very sorry to say to everybody that this is actually coming up to the end of the show. So thank you everyone for joining us on air, and thank you for everyone for joining us in Second Life. Many, many thanks to Remy Ware, Alistair Wilson, Richard Lenski, Alison Pern and Malcolm Love. And also thanks to our production team, Diana O'Carroll, Tom Simpkins and Petro Minch. Now for next week's show, we're looking about body clocks. So you will need to set your alarm, regardless of whether you're a night owl or a morning lark. We're finding out about the circadian rhythm. Now if you've ever been jet-lagged after a very long flight, then you'll know how out of sorts you can feel when your body clock is out of sync. You don't know when to eat, you don't know when to sleep, but you do know that you should tune in next week to find out how circadian rhythms work and why they do go wrong. So if you've got any questions for us, you can get them into chris@thenakedscientist.com and we'll give them a go. Or you may have a question that you think needs some special attention, so you want to get that one into question of the week at thenakedscientist.com, where the wonderful Diana O'Carroll will handle it it for you. Now, one other thing that we should mention is that we have been nominated for a European Podcast Award. We're very, very pleased to have been nominated, but we will need your votes in order to win. So please, if you can, go to thenakedscientist.com/vote, where you'll take you to a link so you can vote for our podcast and we can win an award. But once again, thank you ever so much for joining us. Thank you to our guests, and have a great week.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.